to you K-Singh man. In this lecture, I am going to explain what is de Moivre's theorem and another concept, the nth root of unity. This de Moivre's theorem has an application in complex number theory. Now let us see the statement of de Moivre's theorem. If n is an integer, then the value of cos theta plus I sin theta power n is cos n theta plus I sin n theta. And if n is a rational fraction, then one of the values of cos theta plus I sin theta power n is cos n theta plus I sin n theta. Now let us see uses of de Moivre's theorem. De Moivre's theorem allows us to compute the powers and roots of the complex numbers. It allows us to compute large powers of complex numbers expressed in polar form without having carried out every multiplication explicitly. It uses to compute the nth root of unity. It also establishes a relation between complex numbers and trigonometry. Now let us see the proof of de Moivre's theorem. We will take three cases: when n is positive, when n is negative, and when n is a rational fraction. We will take all these cases one by one. Case 1, let n be a positive integer. Now concentrate on the multiplication. Cos theta 1 plus I sin theta 1 into cos theta 2 plus I sin theta 2. If you multiply these entities, you will find cos theta 1 plus theta 2 plus I sin theta 1 plus theta 2. If you take such three entities, cos theta 1 plus I sin theta 1 into cos theta 2 plus I sin theta 2 into cos theta 3 plus I sin theta 3, you will have the result cos theta 1 plus theta 2 plus theta 3 plus I into sin theta 1 plus theta 2 plus theta 3. If you proceed in the same way up to n steps, that is multiplying cos theta 1 plus I sin theta 1 into cos theta 2 plus I sin theta 2 into cos theta 3 plus I sin theta 3 and up to cos theta n plus I sin theta n, you will have the result as cos theta 1 plus theta 2 plus theta n plus I sin theta 1 plus theta 2 plus theta n. So what you are visualizing over here, that the angle term after the multiplications are getting added and all. Call this relation as equation 1. Now if you do a small substitution, that is put theta 1 equal to theta 2 equal to theta 3 equal to theta n equal to theta, then your equation 1 will convert into and give a result as cos theta plus I sin theta power n equal to cos n theta plus I sin n theta. And this is the de Moivre's theorem for the positive integral power of n. Thus de Moivre's theorem is verified for the positive integral values of n. Now case 2, let n be a negative integer. In this case, let us suppose that n equal to minus m, where m is a positive integer. Now cos theta plus I sin theta power n equal to cos theta plus I sin theta power minus m, and according to the law of index, we have 1 by cos theta plus I sin theta whole power m, and we have just seen for the positive integral value of n, the de Moivre's theorem is verified, so it will be equal to cos m theta plus I sin m theta. Now after rationalization, we have a result cos m theta minus I sin m theta by cos m theta whole square minus I sin m theta whole square. And initially we have taken n equal to minus m, so m equal to minus n. Now substituting the value of m in this relation, finally you will have cos n theta plus I sin n theta. So what we have obtained here, that cos theta plus I sin theta power n equal to cos n theta plus I sin n theta, where n is a negative integer. Thus in this way our de Moivre's theorem is verified for negative integral value of n. Now case 3, we will take n as a rational fraction. Let n be a rational fraction and take n equal to p by q. And from the definition of the rational fraction, we know that p and q are integers, where q is a positive integer and the HCF or GCD of p and q is 1. So according to definition, this q is positive, and we have already seen that the de Moivre's theorem is verified for the positive integral index. So the value of the expression cos p by q theta plus I sin p by q theta whole power q equal to cos q into p by q theta plus I sin q into p by q theta. This comes out to be cos p theta plus I sin p theta, and we have already seen that this de Moivre's theorem also holds for negative integral power. So this expression cos p theta plus I sin p theta can be written as cos theta plus I sin theta whole power p. Now taking qth roots both sides, we have one of the value of cos theta plus I sin theta power p by q is cos p by q theta plus I sin p by q theta. And to find all the values of cos theta plus I sin theta power p by q, we will use the relation which I am going to tell you. Cos theta plus I sin theta power p by q equal to cos theta plus 2 pi r plus I sin theta plus 2 pi r whole power p by q. And here there is no harm in writing such expression because cos and sin functions are periodic with period 2 pi. So finally what we have got, cos theta plus I sin theta power p by q equal to cos p by q into theta plus 2 pi r plus I sin p by q into theta plus 2 pi r, where r varies from 0, 1, 2 up to q minus 1. Here r is any integer. Now putting r equal to 0, 1, 2 up to q minus 1, we will have these n expressions as shown on your screen. If you put r equal to q and use the property of periodicity of sine and cos functions, you will have an expression which is same as the first expression. If you put r equal to q, q plus 1, q plus 2, etc., the same set of values will repeat over and again. So what would you conclude over here? We have only n distinct set of values. Rest values are repeating again and again. Now let us see the algorithms to use the de Moivre's theorem to find the powers and roots of a complex number. Step 1. Suppose we have a complex number z equal to a plus ib given in the Cartesian form. Step 2. Convert this complex number into the polar form by substitution a equal to r cos theta and b equal to r sin theta. Step 3. You will have the complex number into the polar form as z equal to r into under bracket cos theta plus I sin theta. There r equal to square root of a square plus b square, which is the modulus of this complex number, and theta equal to tan inverse b by a, which is the argument of the complex number. Now to find nth power of a complex number, use the de Moivre's theorem as shown on your screen as z to the power n equal to r to the power n under bracket cos n theta plus I sin n theta. Similarly, to find the nth root of the complex number z, use the de Moivre's theorem as shown on your screen as z to the power 1 by n equal to a small r to the power 1 by n into under bracket cos 1 by n into theta plus 2k pi plus I sin 1 by n into theta plus 2k pi, where k equal to 0, 1, 2, 3 up to n minus 1, and in this way you will find n different roots. Here one thing you visualize that the modulus of each of these roots is equal to non-negative real number a small r to the power 1 by n, whereas the argument of each of these roots differ by a multiple of 2 pi by n into k, where k equal to 0, 1, 2, 3 up to n minus 1. Now let us see the nth root of unity. Now exploiting the formula for the nth root of complex number which we have just obtained by using the de Moivre's theorem, namely z to the power 1 by n equal to a small r to the power 1 by n into cos 1 by n into theta plus 2k pi plus I sin 1 by n theta plus 2k pi, where k equal to 0, 1, 2 up to n minus 1. Here r is the modulus and theta is the argument of the complex number z. Call this relation as equation 1. In case of nth root of unity, we have the modulus of complex number as 1 and argument of complex number as 0. Accordingly, to find the nth root of unity, we will substitute r equal to 1 and theta equal to 0 in the equation 1. Then we will have the relation for the nth root of unity as nth root of unity equal to cos 2k pi by n plus I sin 2k pi by n, where k equal to 0, 1, 2 up to n minus 1, and call this relation as equation 2. And if you call these n roots of unity as z0, z1, z2, zn minus 1, then you will have a relation of the type as shown on your screen. You will see the values of z0, z1, z2, zn minus 1. If you visualize the equation 2, you can say that the modulus of each of these nth root of unity are same, which is equal to 1, but their argument differs by a multiple of 2 pi by n into k, where k is 0, 1, 2 up to n minus 1. Now let us understand by geometrical point of view what these nth root of unity z0, z1, z2, z3, zn minus 1 represents. You will find these n roots corresponds to points in the complex plane as the vertices of a regular polygon of n sides inscribed in a circle of radius 1 and center at origin, that is z equal to 0, as shown in the diagram. Let us see one more thing. If you say z1 equal to alpha, then you can represent rest of the n minus 1 roots as the power of alpha. For example, z2 equal to alpha square, z3 equal to alpha power cube, zn minus 1 equal to alpha power n minus 1, and naturally z0 equal to 1, you can write alpha power 0. Now let us see two more properties. The sum of the n roots of unities is equal to 0, that is z0 plus z1 plus z2 plus zn minus 1 equal to 0. And next, the product of these n roots of unity is equal to minus 1 to the power n minus 1. Now thank you for watching UKSing Maths. If you wish, you can like and subscribe UKSing Maths, our YouTube channel, to stay connected with us. You are free to comment on the content of the article and suggest any improvement if any. Your suggestions are always welcome and highly appreciated. Thank you.